And we are back. All right, so this chapter is all about kinetics, which has to do with the rate of a reaction. So last chapter we talked about thermodynamics and if a reaction will occur without outside intervention. So if a reaction is spontaneous. But the main difference I want to make is spontaneous does not mean fast. So an example of a reaction that's spontaneous is the transformation from carbon in diamond form to carbon in graphite form. So that reaction is spontaneous, but it's so slow it is not detectable. Okay, and there's a couple of other useful reactions, like the production of ammonia, which is known as the Haber process. So what we're able to do is change the conditions, like increasing the temperature, changing the concentration, or later in the chapter we're going to talk about catalysis, where if you're adding a catalyst, it helps to lower the energy you need in order to do that reaction, so it enables the reaction to go faster. Okay, so with the lab, we already talked about reaction rate, and it is change in concentration per unit time. So we put it as change in concentration over change in time. And remember, with these brackets, those brackets indicate molarity, moles over liters, which is our unit of concentration. So anytime you're given concentration, usually it will be in terms of molarity or moles over liters. Okay, so kinetics always deals with the speed of a reaction. And one thing I do want to point out is that with this concentration of a reactant or product per unit time, think about in this reaction, we have the decomposition of nitrogen dioxide. So the concentration of this reactant of NO2, that concentration decreases over time because it's going away. You'll notice all these numbers as we're going down, those numbers are decreasing, whereas both the two products, NO and O2, those are products, those concentrations are over time, so those are increasing, whereas, I can fix this one, the NO2 is decreasing over time. Okay, and what we can do is we always are going to make the reaction rate a positive quantity. So reaction rate is always going to be positive. So we can modify this equation. We will put a negative in front of it if it's for a reactant in order to make reaction rate positive. Looking at this reaction, if we wanted to look at the comparative relative rates of all those, what we can do is for NO2, since it's a product, it's negative of that change in concentration over the change in time. And if you look at the coefficient of NO2 and NO is the same. So for NO, it's still the delta NO over change in time, except now this is positive since it is being produced, since it is a product. Then, if you look at the coefficient in front of the O2, that coefficient is only 1. So that means when we're looking at the change in concentration of O2, or this rate is half as fast as NO2 and NO, since those coefficients are 2, and the coefficient of O2 is only 1. So that means this is half as fast. So in order to make these equivalent, we have to multiply this by 2. Okay, so essentially you're multiplying by whatever the inverse of that coefficient is. And still here, this is a product, so that is a positive value. Okay. And using this data, you should be able to calculate reaction rate. So let's say I wanted you to calculate the rate at which the concentration of NO2 changes over the first 50 seconds. Okay, so automatically we know for NO2, it's the negative change in concentration of NO2. So if we look at those first 2 columns for NO2, it's the negative of the final concentration, which is 0.0079. And all these concentrations here are in molarity, or moles over liters, minus the original concentration, which is 0.0100 moles over liters. Okay, then it's divided by the change in time, so final minus initial, so 50 seconds minus 0 seconds. Then when we divide that out, since this is in the parentheses is going to be negative followed by a negative, our result's going to be positive. So you'll get positive 0.000042 moles over liters times seconds, or, so you'll either see that or it in scientific notation, so 4.2 times 10 to the negative fifth. And you'll either see the units in terms of moles over liters times seconds, or you'll see it in terms of molarity, moles over liters times inverse seconds. Okay, so for all those are instantaneous rates. So if you look at this graph, the concentration of NO2 is decreasing, like so, except that's not decreasing at a constant rate. It's not a straight line down. Okay, so it's tough to find the actual rate at a given point in time. So what we have to do, if we want the actual rate at time, let's say 100, so this point right here, we need to make a line tangent to that slope and figure out the slope of that line, and then we can figure that rate at exactly 100 seconds. What we just calculated was the average rate over the first 50 seconds. Okay, so average rate is when you're talking about change in time. Instantaneous rate is the rate at a specific point in time. And you'll notice here the curve for NO2 is the exact same curve as it is for NO. The NO is just inverted, is just flipped, since NO2 is a reactant, NO is a product, and they have the same coefficient. Whereas O2, yes, it's a product, so its concentration is increasing, but it's increasing at a slower rate than NO, and its rate that it's increasing is exactly half of NO. Okay, so with these instantaneous rates, it's the rate at a particular point in time, and you get it from getting the tangent to the curve at that point. So at that point, 100 seconds, if you look at that math right there, so the difference, the slope of that line, the change in y, in this case, the concentration, that change in y is 0.0026 moles over liters. And then that's at 110 seconds. So then the time is 110 seconds. And that is equal to 0.000024 moles over liters times seconds. And if you'll notice, when we calculated our rate for the first 50 seconds, that was higher than the rate at 110 seconds, because as the reaction is progressing, the rate of disappearance of NO2 is decreasing. So what we can do to show how fast these reactants are disappearing and how fast these products are appearing are by writing rate laws. So it shows how the rate depends on the concentrations of the reactants. So for now, we're just going to consider the forward reaction here and not the reverse reaction. Next chapter, we'll talk about the reverse reaction. Every chemical reaction is reversible, and both the forward and reverse reactions occur, but we're going to delay that thinking for now and just think about the forward reaction. Meaning, the rate just depends on the reactant and not on the products. Okay, so we are ignoring the reverse reaction because we are just studying the point right as soon as the reactants are mixed. So that means in this reaction, the only reactant is NO2. So the rate is dependent upon that concentration. Remember, those brackets mean concentration. And these other two things, the K is the rate constant or proportionality constant for that particular reaction. And we'll go over how to get that next class. And then you have the order N of the reactant. And the one thing I want to point out is this is not necessarily the coefficient in that balanced reaction. So just because there's a 2 in front of the NO2, that doesn't mean the order of NO2 is actually 2. And we'll go over how to obtain that value next class. Okay, so the concentrations of the products don't appear because the reverse reaction does not contribute to the overall rate. We're only studying it right as soon as those are mixed. Okay, so a couple of things. I do want to go over how to get the units of each one of these. So rate, we know, is moles over liters times seconds. K, we don't know the units. Then NO2, that concentration, is in moles or liters. So our units of K are dependent on what the value of N is. Okay, so if N equals 0, that means that NO2 to the 0 power, that means those units don't exist. So that means the units for K are moles, the same as they are for rate, moles over liters times seconds. However, if N equals 1, so it's just the units of concentration, if N equals 1, if we rearrange this and solve for K, we're dividing each side by moles over liters. So that means these moles cancel, these liters cancel. So now, if N equals 1, that means the units of K are inverse seconds. Okay, then if N equals 2, now it gets a little more challenging. So now our rate is still moles over liters times seconds. And here, if n is 2, it's moles over liters squared. So that means what we have to do, divide each side by moles over liters squared. So moles squared over liters squared. And you'll notice, okay, the square will cancel out with the mole. Liters squared, the square will cancel out with the liters. So that means it's inverse seconds over moles over liters. So if you flip that, that means the unit of K is liters over moles times seconds. And then last one, if n equals 3, so that means it's moles over liters cubed to the third power. Now, since you're dividing each side by moles cubed, then it becomes moles squared down here, liters squared down there. So that means K, the units are liters squared over moles squared times seconds. So it's important, you should be able to derive the units of K depending upon what this value of n is, what the order of that reactant is. Okay? And the main thing, this value of n, it has to be determined by experiment. Okay? It is not written from the coefficient from the balanced equation. So like for this one, do not assume n equals 2 here. Okay, just because 2 is the coefficient in front of NO2. Okay, so now this is the first type of rate law, and when we are referring to a rate law, normally we're going to assume it's a differential rate law, which is dependent upon concentration, which is just how we just wrote that rate for this reaction. So this is the differential rate law. So rate as a function of concentration. Then the integrated rate law, it shows how concentration is dependent upon time. So how we wrote the rate law earlier for the change in concentration of our reactant NO2 over time. So that's the integrated rate law. It's how this concentration changes over a function of time. So the differential rate law is just concentration. Integrated is how that concentration depends upon time. Okay. And the main thing here, most reactions do not occur in a single step. Usually, they undergo some type of, we call mechanism. Okay, which is a series of steps by which a reaction takes place. Okay? And what happens is this rate law, this differential rate law, helps us to understand and infer these steps by which the reaction occurs. Okay, so that's the advantage of the differential rate law, and we get that from experimental data, which we're going to talk about next class. We learn what these actual steps are, and with the industrial production of ammonia, is if we're producing it on a large scale, how can we make it more efficient? How can we make this reaction occur faster? So what we do is we speed up that slowest step, which is called the rate determining step, because that's the step you need to speed up, and we determine, okay, do we need to increase the temperature or decrease the pressure or add a catalyst at a certain step? So knowing this rate law is extremely important to understand how fast that reaction can occur and how we can make it faster. All right, that's all for today. See you next time.